Welcome back to ECE 442-542. As way of announcement or announcements, Homework 7 is now posted and it's due a week from Thursday, giving you a fair amount of time to do that. Homework 8, I'm deciding what we will do for Homework 8. Your project, if you're in 542, is due on the Saturday before, the Saturday before the week that final exams begin. And we have our final exam on the first day of finals on Friday evening from 6 p.m. to 8 p.m. And I want to make sure that everybody gets that announcement. The other announcement, you've probably received emails, is that true, about the TCEs that you can fill out online. 2 of you have already filled that out as of early this morning. I don't know if I should have announced that. The exams are graded, so we'll see how that correlates with the graded exams and the TCE. Maybe I should have waited a day or 2 on the TCE announcement, but you should have received, because have you received email notification that your TCEs are available to be filled out online? I will not be doing that in class, but that is important. I like to get that information, and I don't see that until grades are awarded, so you don't have to worry about that influencing positively or negatively your grade. As far as our plan for today, I would love it if we would get this far into it. I don't think we will. I want to have another consonant. I want to do the D part, the PID now, today. We'll look at the structure of the PID controller, give some examples of the controller approach once we have one more parameter available. Then that leads us really into a generic controller design, and in that sense start thinking about having a zero shaker and a pole shaker, and you're now sprinkling zeros and poles somewhere on the z-plane to your advantage so that you can move the root locus branches, all of those simultaneously for some gain k inside the unit circle, so that you can get stability and hopefully the dominant behavior that you want. That's what I'm meaning by generic controller design, which really refers to where do you place your poles and zeros of these controllers. And it doesn't have to be restricted to a PID structure. That may naturally lead us into a state space control design, which is maybe a more turn the crank. Maybe you'll start saying, where do I put these poles and zeros? I don't quite see where to go. Well, then you try a state space design approach, and it will sort of tell you what you might have tried given a transfer function based controller strategy. That's where we're headed. Let's see how far we can get. And I may jump back and forth between what I call my controller transfer function. I might call it a D of Z, or I think we've been calling so far this semester C's. Is that true for our controller? I kind of forget from day to day, but wake me up or remind me or just bear with me. If you know, you should know by context what I'm meaning by the controller transfer function. Here is our system, and now what we want to do is in that, and you should notice that I am being open with what domain I'm dealing with. It doesn't really matter whether I'm in the continuous time domain or the discrete time domain with respect to this block diagram. Obviously, it depends on which domain you're in on the analysis that you're performing. But a PID controller, in terms of what it looks like in the analog setting, you have a proportional gain, K sub P. You have an integral gain or an integral term that's dealing with previous air behavior. The proportional is dealing with the present air signal. The integral term is saying what's happened in the past. And the derivative piece, which is what we will look at today in combination with the others, the P and the I, the derivative piece says, what can I expect? Or it's sort of an anticipatory control piece. And you may see this written many different ways, and that's why I'm saying I'm going to scroll through this quickly, and then we'll slow down and see where they came from. But you might have it written as a gain that scales all three pieces. The first piece being the proportional piece. The second piece, again, is associated with the integral behavior of your controller. And the last piece, the third piece, is this derivative piece. Some books or sources might combine the K sub I over K sub P into one constant T sub I. And T sub I is scaling S, and S is a frequency or sort of an inverse time, and so the T times S, T sub I is a time variable. And we'll call this the integral time. T sub D is scaling the S. Again, that's T times S. That's going to be non-dimensional. And now you have a T sub D is also a time. So you could have the derivative time. And this is then maybe what you might see in certain representations or presentations of a PID controller for an analog control setting. You have the proportional gain, which scales all three pieces, and you have a proportional piece, an integral piece that is influenced by the integral time, the derivative piece, which is influenced by the derivative time. That's our structure. What we want to do is figure out how to take that into a discrete or a digital form. And you can relate the different terms in the two domains if you keep track of the proportional gain, K sub P, or K, I guess, in the last description. That K, T sub I and T sub D now weight or scale these three air terms that are the air at the present time, the air one time step earlier, and the air signal two time steps before. The only other unknown gain or the variable in that expression is capital T, which represents the sample period. The first thing we want to do is figure out how do you get from something like this, C of S, into, you could now Z transform this and obtain a C of Z. Let's see where this difference equation comes from. That's our first goal for today. We want to see how to go from capital C of S, the analog version of our controller, to the digital form. How? And we could do that many different ways. And we'll just show one way to do that that will give us that most recent form of the PID, the discrete time PID controller. Here's C of Z that we had before, and that's just the transfer function between the air signal and the command, the input signal going into your plant. The last way that we represented that was with this description, K times 1 plus 1 over T sub IS plus T sub DS. Let's put all three of those over a common S, or let's factor an s out of the denominator of all three of those terms. Meaning, now let's say we have a k over s, and what now needs to happen? Well, the 1, to preserve that, we need to introduce an s in the numerator. We already had a s in the denominator of the middle term, and so the middle term now becomes 1 over t sub I, and the t sub d now needs to be scaled by s squared, such that if we scale it by k over s, we end up with the original k t sub ds that we had before. Now what I want to do is relate the input signal u and the air signal e, which in a control setting, the E is the input, the air signal is the input to our controller, and the input to our plant is the output of the controller. Can I confuse you anymore? But you know that, right? The transfer function is input over output. Or maybe I should say output over input, but in this case, the output's the input and the input's the air. Did I say that right? We'll have to do that on a video or something. Well, we are doing that on a video. Wow, you can just hit replay, rewind, and never mind. All right, now let's cross multiply and relate the input and the output of our controller. Or multiplying both sides by s, we have s u of s is equal to k s plus 1 over t sub I plus t sub ds squared e of s. If we now put that back, that's in the frequency domain. If we put that into the time domain, multiplication by s is just a derivative. And so now we have the derivative of the input, which is the output of our controller. Then we have k times the derivative of our air signal plus 1 over t sub I e of t plus t sub d second derivative of the air. Maybe I should have used some different brackets so that we can distinguish between arguments of E and its derivative. Questions on that? That should be just a straightforward frequency domain to time domain transformation. Now we need to discretize that. And we have many different ways. We've looked at many different ways of finding discrete equivalence. Let's use one for this case, which is the backward Euler discrete equivalent, which means this derivative is going to be u at the present time minus u one time step before divided by the interval between those two sampled values of our output of the controller. That's just the discrete backward Euler approximation of the derivative. Shouldn't be a problem. Now we simply have to do that a few times, but we have to do it really a couple of times when we come to the second derivative. But let's just do that in pieces. So now I have k, and I have to sort of observe this square bracket. I now have e of n minus e of n minus 1 over t. That's the e prime, plus 1 over t sub I e of n. And now I need to hit carriage return. I'm still inside the square bracket, and I now need to have plus T sub D, and I'm going to do this in 2 steps. So the first step, I'm going to differentiate or approximate the first part of the second derivative, meaning I now have e prime of n minus e prime of n minus 1 all over t. And to put all of this together, I need to get rid of those e primes. Meaning, let me now replace what's in the curly brackets with a derivative approximation for each of those e's. Meaning, the first piece is going to be e of n minus e of n minus 1 over t. And all of that is over t. Is that okay? That's just the e prime of n. I've now differentiated or approximated that derivative minus the approximation of e prime of n minus 1, which is just e of n minus 1 minus e of n minus 2 all over t. And if you now introduce or insert this curly brace or curly bracketed expression for that green curly bracketed expression, multiply everything together, factor all the pieces, you will end up with the expression that we just wrote down to begin the class. In the time domain now, we end up with our relationship between the air signal and the input to the plant as U of L. Well, I don't know why I switched from U of N to U of L, but I did just to keep you awake. So this is now U of N. I'm going to multiply both sides through by T, and I'll have U of N equal, and I'll put this over on the other side. And I now end up with U of L minus 1 plus all of these other pieces. I have plus K E of N. I probably have another E of N right there with 1 over T sub I. And I have another E of N here that actually gets divided by T. So I have 3 E of N terms, if that made sense. I have now a K times 1 plus T over T sub I plus T sub D over T E of L. And if you do the same thing, I'm still inside the square bracket, but now I'm collecting all of the L of n minus 1 or E of L minus 1 terms, and that will give me 1 plus 2 T sub D over T. And you can, I know you're just dying to see this, so go home tonight and make sure the algebra is correct. Okay? We're not going to spend a lot of time trying to verify the algebra. And just see if there's an error. That's fine. Just come see me in office hours and correct me. And then we will correct it for everyone in class. But hopefully you can verify or validate that you now have this description of a PID controller. It relates the air signal. So now we have to, the PI controller really only had 2 terms in it. We only had the air and the air 1 sample period before. With the PID controller, we now have to worry about the air 1 sample period before, and the air 2 sample periods before. So we're storing 2 different previous air signals if we were implementing this controller. This is just a difference equation, and you should be able to program this up in any kind of computing system if you know the T's, TI, TD, and T, and the gain K. And that's what we will start looking at trying to derive. But I'm getting tired of all these t's. So I'm going to clean it up. I'm going to just call this an alpha 0. This, with the minus sign included, is going to be an alpha 1, and this will be an alpha 2. Meaning if I can't make up my mind. I don't know whether I want to be in the time domain or the transform domain. Let's go back into the transform domain. I'm just making sure you guys are keeping track. If I z-transform the left-hand side, what do I have? That one's a hard one. Not. What happens if I z-transform u of L? You don't even need a coin. It's u of z, right? Now, if I z-transform a one sample period delayed version of u, what's that going to be? Oh, now you get on it. Right? And now let's use the alphas so that now I have k alpha 0 e of z plus alpha 1 z to the minus 1 e of z plus alpha sub 2 z to the minus 2. I'm cheating. I'm widening my paper. Virtually. E of z. We okay with that? I just replaced all those t's and t sub d's and t sub i's with alphas, so I didn't have so much to write. But it's the same structure. And now I want to obtain a transfer function between the error, e of z, and the input, u of z. And that will give me my controller's transfer function in these variables. Let me collect all my u terms, 1 minus z to the minus 1 on the left. And on the right, I have k times alpha 0 plus alpha 1 z to the minus 1 plus alpha 2 z to the minus 2 e of z. Or this is now my transfer function of my controller in the discrete time setting, u over e. I'll divide through by 1 minus z to the minus 1, or, yeah, so that now I have k alpha 0 plus alpha 1 z to the minus 1 plus alpha 2 z to the minus 2 all over 1 minus z to the minus 1. But typically when we talk about transfer functions, we're not dealing with negative exponents, are we? We like to have positive exponents. We can factor out a z to the minus 2 upstairs and downstairs and cancel those. Or we can hit both sides with, or both top and bottom with z squared. And we end up with downstairs z squared minus z. And upstairs we have k times alpha 0 z squared plus alpha 1 z plus alpha sub 2. And the denominator, this is what? This is a PID controller. And now we can see in our PID controller, the poles are fixed. If we are implementing in this class for this semester, we'll just agree that if we have a PID controller, we're going to have a pole at z equal 1, that's good. That's consistent with our integral controller from before. And now we have one more pole at the origin, and that keeps this controller causal, because our numerator is second order and our denominator is second order. And what do we have upstairs? I really didn't specify, well, I will design those alphas, meaning you could now think of this C of z, which is u of z over e of z, is now some gain k bar z minus beta 1, z minus beta 2 all over z, z minus 1. Is that okay? I just have an arbitrary second order numerator, which really says I have two factors. And the beta 1 and beta 2, those could be two real poles, or they could be selected to be complex conjugates of each other. I might have two complex zeros that I want to build or that I want to design in this PID controller. But the PID controller, once I've said, oh, I want a PID controller, you can immediately write down this denominator. You have a zero, a pole at the origin and a pole at z equal 1 for this structure. If you're looking now at the pole zero diagram, which now every time you see a transfer function, don't you just see x's and o's? Even you close your eyes, you could just be in deep concentration. I'm just thinking, Dr. Tharp. Okay, I believe you. What do you see on the back of your eyelids? X's and O's, right? If I start talking transfer functions. If you now looked at the pole zero diagram of this PID controller, what do we have? Well, we have a pole right there that we will add automatically. We will automatically add a pole right there, and that pole there does what for us in terms of our accuracy, steady state accuracy? That helps us, doesn't it? But it makes it a little bit more challenging in terms of our transient response. There's this trade-off that we have to worry about. And then what else? Now we have two zeros, and those zeros could be here and here. Let's say at beta 1 and beta 2, those are design parameters. We get to pick where those betas are located. Or they might have been here and here. Meaning if you see the black, don't look at the red. If you see the red, don't look at the black. So I'm going to erase one of those. But, got a little too anxious with my eraser. But these are up to the designer. That's you. They're up to the engineer. You get to pick where those two zeros are sprinkled in the z-plane. You can't move the x's in the PI controller. One is at the origin, the other one's at 1. But the zeros you get to play with. And what are you playing? How are you playing with those zeros? You're using those to shape your root locus so that all the branches of the root locus come into the region that you want simultaneously. You want all the branches of the root locus inside the unit circle for sure, but then you want two of those branches to dominate the behavior, and those are going to be what you see in terms of your response from the system. Yes? So the question was, will the PID controller always have a pole zero excess of 0? And the way that we are designing it Yes, in this class. We're going to go ahead and assume that we're going to have two poles fixed, one at the origin and one at 1, z equal 1, and then two zeros. Now, if you pick those zeros, you could potentially maybe have a generic, how do I want to say this? A more generic PID or a less complex PID to where you make one of those betas 0, then that Z cancels the bottom Z and you now have a PI controller. So you've given Vanna back the D. Nobody's playing along. Who's the other host? What is that, Wheel of Fortune? Yeah, so maybe we give back the D. Maybe you don't need the derivative. That's how you could lose, but you still have a pole zero excess of 0. Okay? If you've canceled the one numerator 0 at the origin and the denominator 0 at the origin. And if you really wanted to, I guess you could say, oh, I can collapse this PID controller down to a P by making beta 1 0 and beta 2 1, and then you just have a gain controller. So you can, by the choice of your betas, make this collapse to a PI or a P. But for now, when I say PID, that's saying, oh, I've got two zeros to play with. That's the idea. Does that help? But all of those end up being a pole zero excess of 0, all of those controllers. Here's a very basic description of how you can design with the PID controller. And I know you all became engineers so that you could design, right? That gets you all excited. Now I can design, right? What do we do? Well, if we're designing with a PID controller, the first step is we actually introduce, or it introduces, two fixed poles. We have one pole at z equal 1, and what does that do for us? If I plop a pole at z equal 1, what does that tell me? It's helping steady state accuracy, isn't it? If I had a type 0 system, I've now made a type 1 system. So this is to help us improve steady state accuracy. And we get that pole automatically when we start saying PID controller. We get a second pole at z equals 0. And this one is to make our denominator the same order as the numerator. We have two zeros, and we need a causal controller. So adding this fast pole, that's a fast pole when it's right at the origin, at 0. This allows a causal controller. That's the first piece. That one is just automatic. You say PID controller, boom, you already have half the poles and zeros placed. That's fixed. Now comes the more design part. Now the designer, which is you, the designer can select two zero locations. And that's one of the reasons why you were trying to become comfortable with the root locus sketching strategy so that you know how to sprinkle those zeros, because that will help you feel or understand or design how those branches are going to come in to the unit circle. And these two zeros, you could have two real zeros or a pair. So should I say two complex conjugate, or should I say a pair of complex conjugates? What would you prefer? What? Two? All right, so now we have two complex conjugate. I don't want you to be confused. This is not two pairs. This is one pair. It's two complex conjugate zeros. Is that clear? All right, now let's start playing. Or, I'm sorry, designing. We're designing now. Let's look at some examples. And if somebody sent you to the whiteboard and said, talk to me, answer the following questions. Start basic. Just start from the ground up. Suppose somebody gives you, so this is examples. Suppose somebody says, oh, I have a plant that's 1 over z minus 0.75. Do you see the root locus or the pole zero diagram? What were we using? Were our plants blue and our controllers red in terms of poles and zeros? Red and blue, we're wildcats, right? We need to stick with the colors. All right, so we'll have, the plant will be blue, and I'll probably forget that, but there's what we have. If the plant's blue, we need to kind of bring them back, right? If they're blue. So we'll put a little red with them and make them more happy. Okay? For those of you following along at home, you're missing all of this. Lucky you, right? All right. So, suppose somebody says, I want steady state error of 0 if I put in a constant. Can you do that with a constant gain controller? Can you produce a steady state error of 0 for any constant input? The answer is a no. So we need a PI controller, and we said we'll go with red. So now we need a PI controller. And the PI controller I told you I would probably mess up. We're supposed to be doing this with C's, didn't we? C of Z. PI controller says I have a pole right there, doesn't it? But now to make my design process easier, why don't I just place that 0 right there, and now I know what my root locus is. It's pretty easy to sketch. My root locus now just goes that way if I now have K. Is that okay? And you can pick K. What will K do? That's going to move you somewhere along this line between z equal 1 and minus infinity, and you probably don't want to crank up the gain to put that triangle outside the unit circle, do you? But you can now locate that triangle to give you the speed that you want, and you can get the gain k necessary to give you that speed. Here, k is selected for a certain speed of response. All right, that's one example, and that one we could get by with just a PI controller if that was our only design spec. give us steady state accuracy of 0 for constant input. We didn't have to do a PID controller. Suppose now somebody says, well, that's not the plant we have now. Now we're doing examples. Okay, just wanted to make that clear. Suppose we now have a system g of z is 1 over z minus 2. And again, maybe we want 0 error due to a constant input. Question? Yes? All right, the question was, I'm confused about the root locus you sketched, right? And what I did is I basically canceled a stable pole. And essentially, when you see that pole 0 combination, I've canceled that pole with a 0. That's like those have been erased. Now you really don't have anything happening there. I mean, you do. You've got a fixed mode there, but it's being zeroed out with your 0. So it's like it's not even there. And now if you found your closed loop transfer function, you would see that you have effectively a first order system, and the pole is wherever you pick K to locate that triangle. So that root locus is just a basic root locus now. It has a pole 0 excess of 1, and that says we have 1 asymptote. Is that okay? So in a real system, there might be some uncertainty. Oh, you guys, are you... Man. Okay, so let's say there is uncertainty. Now I'm going to have to... Okay, I'll pay back. Now look at this. Can you cut your page and paste it? Somebody's wanting question after the fact. All right, so the question was, now I forgot the question, I got so excited. Here's 1, and we had a pole right there, didn't we? And we thought we had it modeled at 0.75. And now somebody says, there was some uncertainty in that, and it actually, let's just be really large with the uncertainty. Let's say the pole was actually more like a half. And we located our 0 at 0.75, and we had a pole right there. So now what's going to happen? What's our root locus look like? Right? So as the uncertainty reduces between the pole and the 0, that gap now goes away, and we essentially now have a pole 0 cancellation. We only really see 1 pole effectively. But if we crank up the gain, we may end up with now a pole here close to the 0, so that sort of goes away, and we have another pole here that's going to be sort of the main pole in our closed loop system. Does that help? And if the 0 happened to be on the other side, oh good, I gave myself enough paper. Suppose now we erred on this side, and our 0 was now here. Now what happens? Now we have a pole here, but you know what this is going to do, don't you? This is going to give you this behavior. That was supposed to be staying on the root or on the real line. I just got so excited I couldn't stay on it. I really didn't have anything before class to make me jittery. Well, I did actually. I had caffeine, so no caffeine, okay? But that's to get me the rest of the way through class. But do you see what was happening? The smaller that air is, the less that perturbation in our ideal root locus is going to be. And if you stand back and look at this from a long distance away, all three of these root loci sort of start looking the same, don't they? The bottom one, the middle one, and that one all start looking about the same. And they really are the same if the pole and the zero cancel. So yes, there could be some uncertainty, but that's not going to really completely mess things up. It's a fairly robust design. So yes, so as you crank up the gain, but you have to be careful because we obviously don't want to crank up the gain so much to get us outside the unit circle. We really want to crank up the gain to achieve a triangle. Maybe we don't even want to crank it up that much. Maybe we just want to crank it up to get us to 0.9. And then we might be in between that cancellation. Here we might still be at 0.9, and this one might have been in, but that's really fast, so it's going to disappear before this dominant pole plays out. And maybe it just so happens that we end up with two complex conjugate poles, but that's okay. They don't have much real part, or much imaginary part. Does that help answer that question? That's what happens with uncertainty, not on the exam, but in real life. Sorry. You don't want jokes about exams, do you? Now what do we want? Now we have an unstable system to begin with. And if we now say that we have a controller, maybe again a PI controller, where are we going to put beta? The zero. We get the red pole by default if we're now controlling it with a PI controller. What do we want? This is where you get paid what you get paid. This is your design. You need beta to be to the left of 1, don't you? And if you have beta over here, or your 0 there, do you see the root locus that's going to result? You'll find a breakaway, and that will form the radius. Now, here's what we want to do. Let's not a priori say that we know where beta is. Let's say, actually, let's see if we can locate some desired poles and figure out what beta needs to be to make that happen. So here's our approach. We know this is what could happen if we put that beta to the left, or the 0 to the left of z equal 1. But what we want to do now is select beta to produce desired a root locus path, and then k, because once you put that 0 down, that establishes your root locus. The k fixes you at some location on that root locus. K is used to fix the dominant poles. Here's the process. Suppose somebody says, by whatever reason, and this might be because of settling time, percent overshoot, and peak time, maybe somebody says, suppose one wants a z delta of 0.9 plus j 0.1. Maybe they say that's what they want for z delta. And if they want one z delta there, then the other one is going to be at 0.9 minus j 0.1. You get the conjugate with it because we're dealing with real coefficients. Now, here's the question. Is it possible to achieve that z delta? So this is a final exam question. Is it possible with PI control? And you don't have to know the answer. You can just analyze the problem and see if indeed you can make this happen. What do we have? We had a plant pole at 2. Somebody says, oh, let's see what happens with a PI controller. So that puts a pole at 1. And now what we don't know is where this 0 is. But we do know that we are wanting to be the root locus branches. We want them to pass through these triangles. That triangle is supposed to be at 0.9 plus j 0.1. That's where the triangle is. And we want to now say, slide this 0 until the root locus passes through that location. And do you see if this 0 was located such that the breakaway point was in the right place, the root locus may bounce around, circle around, and go right through that triangle. Is that clear? We now just need to figure out, where do we put this 0? And to talk about this, what I'm going to do is I'm going to have, well, if this triangle is on the root locus, what do we know happens at that triangle? Okay, so I'll give you more of a hint. Is there a condition that must be true if we want that triangle to be a closed loop pole? Then it needs to belong to the root locus. How do we guarantee, or how do we check whether a point is on the root locus? What condition? The phase angle condition, don't we? We need the phase to equal what at that triangle? Minus 180, don't we? Meaning, we need to look at this angle. Let me call that theta sub P1. We need to look at this angle, and we can calculate those because those poles are fixed, aren't they? This is now theta P sub 2, and we need to figure out what this angle needs to be, and we'll call that theta sub Z. We're going to now use the phase angle condition to solve for theta sub Z. And if theta sub Z is between 0 and 180, well, actually, we don't want it to be over here, do we? So we want it to be just shy of that z equal 1 point to guarantee that we'll have a closed loop system that's stable. We're going to now use the phase angle condition to find beta, and this is located at beta. Really, we're going to use the phase angle condition to find theta sub z, and then we're going to go back to high school and use trig to find beta, or kindergarten, or wherever it was that you had trig. I don't know. This new math, I never know where you're having it. what do we have? We have our phase angle condition says theta sub z, the angles of our zeros, and we only have one of those, minus our pole angles, is minus 180 degrees. Is that clear what I'm doing now? This is the phase angle condition. We have all of our zero angles, and we only have one zero. That's the red circle. We have two poles, the pole due to our integrator and the pole due to our plant, and they will both contribute an angle. And then all of those need to sum to minus 180 for those triangles to be on the root locus. So if we just were doing a back of the envelope, what's theta sub p sub 2, roughly? Real crude. It's almost 180, isn't it? Because it's way over there to get to that triangle. So let's say that we just are trying to think about this right now. Suppose we say theta sub p sub 2 is approximately 180. What's theta sub p sub 1? We walk to the left a tenth of a unit. We walk up a tenth of a unit. That acute angle is 45 degrees, and we subtract that from 180, so theta sub p sub 1 is 135. So theta sub p sub 1 is 180 minus the inverse tangent of the vertical displacement over the horizontal displacement. That's 135 degrees. If we were dealing with that actual 180 for theta sub p sub 2, then theta sub z minus theta p1 minus theta p2 is equal to minus 180. Then theta sub z is 135 degrees. And where does that put our zero? But thankfully, that theta p2 is not quite 180 degrees, is it? Theta p sub 2 is a little less than 180. So that's going to give us this zero a little bit to the left of that pole at z equal 1. That's the idea. So let's look at the actual theta sub p sub 2. Now I'm just writing down what I tried to illustrate. With the actual theta sub p sub 2, we should be able to find a beta value that's going to allow us to get through that triangle of 0.9 plus j.1. Theta p sub 2 is now 180 degrees minus the inverse tangent. So now I'm just having to deal with the acute angle, the one that's less than 90. I need to go up a tenth in the vertical direction, and how far in the horizontal direction. My pole was at 2, and I need to get all the way back to 0.9. So that's a horizontal distance of 1.1. Is that clear? So I'm looking at this angle theta sub p sub 2 is 180 minus some small wedge, and that small wedge has a vertical distance of 0.1 because we are at j 0.1, and it has a distance away from 2 of 1 plus a tenth, or 1.1. And if you calculate this, this ends up being 5.194, not very big, so that we now have theta sub p sub 2 is 174.8 degrees. If we now use that in our phase angle computation, we have theta sub z minus theta sub p sub 1 plus theta sub p sub 2, which I'll go ahead and write in this expanded form. Or if I now solve for theta sub z, the 180s cancel, or the minus 180s cancel on both sides, and theta sub z becomes 135 degrees minus 5.194, or 129.8 degrees. And we're using that to try to compute beta. Meaning, now we know that this triangle is right there at 0.9, and this is a distance of j 0.1, and the 0 is such that that angle, theta sub z, is bigger than 90 degrees. It's 129.8 degrees. Meaning, I may like to work with this acute angle right here, which I'll call theta sub z bar, and then I can compute that distance x bar. I know theta sub z is related to theta sub z bar by 180 degrees. They're supplementary angles. Am I using the right terms? Yes, no? Anyway, we can evaluate for theta sub z bar. We know what that is. And we know the vertical distance in this right triangle, and we can solve for x bar to obtain beta. This is what we're looking for. We're trying to find that location beta, and we know that 0.9 plus x bar is equal to beta. Is that right? And what is theta sub z bar? That's 180 degrees minus theta sub z, which ends up being 50.194 degrees. So that now if we take the tangent of that angle, that should equal the vertical displacement over the horizontal. And the horizontal was just x bar. And the only unknown in that equation now is x bar. And this ends up being 0.08333. If we look at this on an expanded scale, here was 0.9. X bar is going to put us right there at beta. That's the idea, because this was our triangle right there. Beta is now this 0.9 plus x bar, or this is 0.9833. And we said it was going to be a little bit to the left of z equal 1, didn't we? And beta now is a little to the left. So that our controller our PI controller is now that. And we found that by using our phase angle condition. Questions on that? Are we finished? You wish. That wasn't a joke. That wasn't supposed to be funny. Why is everyone laughing? But did everyone get this far? Are we okay with this? And if you don't, play with it a little bit tonight or before the final, obviously, and before the homework so that you feel comfortable with this. We're now using our root locus construction rules to actually design controllers. How do we find K? We're not quite done. How do we find K? We now know that the root locus is cooperating with this choice of 0. We had a pole there, our PI controller put a pole there, and it now put a 0 right next to that at 0.98. And we actually know that the root locus is going to be such that the root locus passes through that triangle. We fixed that 0 to make this happen. We forced that root locus to pass through the triangle by making that 0 force the phase angle condition to have a phase of minus 180 right at that triangle. That was by design. Now, how do we get the closed loop poles to actually be on the triangle or live on the triangle? We know that at some point they pass through the triangle, but what are we doing? How do we get them to stop at the triangle? The magnitude condition. We now need to crank up the gain K such that these two poles come together, these two branches, they break away, and now we need to crank up the gain to get us to that location. So now that's the question that we're answering. What is K? And we're going to find that from the magnitude condition. And our magnitude condition says we take the controller and the plant, and that magnitude equals 1. So we have K, Z minus 0.9833 over Z minus 1. That's our controller. Our plant was 1 over Z minus 2. And based on the characteristic equation, or the denominator, that's 1 plus C of Z, G of Z equaling 0. We solve that, it becomes equal to minus 1. We find its magnitude is 1. We can now solve this for K. It's now Z minus 1, Z minus 2, all over Z minus 0.9833. And now what do we do? That's the expression for our gain. How do we find K to get us to the triangle? We just plug in the Z value at the triangle, don't we? We force the Z to be what the triangle is. So we now evaluate this at the triangle, which was 0.9 plus J.1. And if you do that, you end up with a gain of 1.2002. And I'm going to actually let you go home and do that. Simulate that and see what happens. You know what you're going to see? My memory serves me, which never trust that. But you're going to have a, what's your steady state accuracy going to be? If I put in a 1, what are you going to go to in the output? 1, because you're using a PI controller and both poles are inside the unit circle. You have a stable response. But this one actually is pretty oscillatory. It goes all the way up. Before it gets to 1, it goes clear up to 4.5, and then it settles to 1. So now we have a 350% overshoot, right? 4.5 minus 1 divided by 1. 350% overshoot. Maybe your boss doesn't like that. May want a different response. I mean, you had great steady state accuracy, but your transient, maybe not so great. So what do? We try a PID controller, right? Because that's going to give us more flexibility. We tried a PI, we spin the wheel and we go D, right? We want a D because we want to spell PID. Have you ever seen on Wheel of Fortune that as a solution, PID? They probably don't have any control engineers on there, do they? That's probably what I would be guessing if I had a P and an I showing up. I'd say PID. And it's probably wanting pi, isn't it? Oh well, never mind. We may not like this response. We now have designed a C of Z that's 1.2002 Z minus 0.9833 over Z minus 1. What's the structure of a PID controller? We just derived it today. It's now some gain, 2 zeros. Those zeros could be real, equal, real, unequal, or they could be complex conjugates. What's our denominator of our PID controller? That's fixed, isn't it? Once we say PID. So that now what we're wanting to do is we now have a pole at 2. Our PID controller forces those two. And now what? We need to sprinkle some zeros down, don't we? One choice might be, I want to kind of keep this as straightforward as possible. What if I just pick 2 real equal zeros? So I'll show them real and equal if I just put them right there. Those are on top of each other, although I've shown them not to be. But what would the root locus look like here? Do I still have this? Do I have a root locus branch on the real line between beta and 1? How about between 0 and beta? So I do have something here, 1, 2, 3, 4. Do I have something between 0 and those betas? No. Do I have anything to the left of 0? How many branches of the root locus do I have? 3. I have 2 that start on the right. What happens? Well, they may not be circles because of this pole over here. But they're going to curve around and stop. They're going to be attracted by those zeros. So those zeros now you can maybe use to your benefit to try to get these poles to not have such a big percent overshoot. Because you had a terrible percent overshoot because that 0 was so close to z equal 1. That destroyed your percent overshoot behavior. We'll have to pick up at this point on Wednesday, but you can go home and start playing.